All right, so the ideal gas law follows this set of equation where you're able to relate the pressure, volume, number of moles of gas, and temperature. And it's basically a way for you to approximate the behavior of many of real gases, whether if you, let's say, change the temperature, change the volume, pressure, or even the number of moles in the gas. Using this equation, you could figure out whatever set of value or variable you're trying to look at. One thing to keep in mind is arc is a constant, and there are basically two forms you could use it for. So one of them is this one right here. And the other one is this one. I'll just make this an approximation, but yeah, so depending on what you're trying to look for, like let's say you're trying to solve for energy, it's better off using this equation, or if you're just looking for volume or specific atmospheric pressure, use this equation. But yeah, I guess one real note to look at is that joules is another way of saying liters times atmospheric pressure. There's many laws in the ideal gas law, one of them being Boyle's law, which basically just means that the number of moles and temperature is constant, which means that for this equation, R is already constant, so it doesn't matter, and it's gone, T is gone. Overall, this means that our initial pressure and initial volume will be equal to our final volume and final pressure multiplied together. And so what this means that let's say for P, we increase it, or for our initial to equal our final, therefore our volume will have to decrease in order to compensate uh, the law. The next law is Charles' law. And for this, number of moles and pressure is constant. So looking back at this equation, we can get rid of P, we can get rid of N, we can get rid of R. We can move this here by dividing both sides by V, or by T I mean. We can get V over T or T over V, however you want to see it. But in the end, we say V initial divided by T initial is equal to V initial, V final divided by T final. And so basically, if we increase our volume, in order for this equation to still be the same, we'll also have to increase our temperature. And now for Avogadro's principle, we say that temperature and pressure is constant. So we can get rid of pressure here. R is gone as usual. Temperature is gone. Therefore, our set of relationship is this. So what this basically means that for our system to be constant when we have constant temperature and pressure, when we increase our volume, evidently we'll have to have more number of moles in our system. So the number of moles will have to increase, and vice versa. If we decrease volume, then the number of moles will have to decrease. And that's just when the number of moles and volume is constant. So volume is gone, N is gone, R is gone. Therefore, we have a relationship where P over T initial is equal to P final, T final. So same thing here. If we increase P, we'll have to evidently increase our temperature of the system in order to keep everything in our system constant, no matter what, and vice versa. One thing to know about temperature is in units of Kelvin. Therefore, if let's say you have temperature of 25 degrees Celsius, you'll have to add 275 to get Kelvin. So basically, let's say Kelvin is equal to whatever number of Celsius plus 273. For this situation here, we'll say 275 degrees Celsius plus 273. K, as in our temperature in Kelvin, is equal to 298 Kelvin. And that's basically what you'll use in your equation for PivNerd.